Hi, welcome to the AICE Chemistry Lecture Series. In this video, we're going to discuss Chapter 4, Section 6, which covers metallic bonding. Now, this is a topic that, again, we saw in Honors Chemistry very lightly, and we're going to go a little more in-depth into it, although metallic bonding is by no means our focus when it comes to bonding. It is in the curriculum, but it is the least discussed form of bonding in the curriculum. That being said, let's take a look at it. Metallic bonding is how metals are held together. Now, when we talk about metallic bonding, we're not talking about compounds like we do with covalent and ionic bonding. We are talking about individual metals. So aluminum, copper by itself, even alloys like brass are held together by metallic bonding. So we're not talking about compounds, we're talking about individual metals, which can be confusing because every other type of bonding that we discuss refers to compounds. Now, looking at the periodic table for a second, it is good to remember where the metals are found. If we look at the periodic table, if we remember that there is what we call metalloid ladder right here bordering boron. So going down in steps, we have our metalloid ladder. Any elements that are found to the left of that ladder are metals. So anything that's to the left of this ladder is going to be a metal. So lithium, beryllium, molybdenum, technetium, platinum, iridium, gold, all of these, including the inner transition metals, are going to be metals. So all of these elements. The only exception to this rule is hydrogen, as well as a few of the metalloids that touch the ladder. So things like polonium is not a metal, antimony, germanium are not metals because those are metalloids. Aluminum, however, which does touch the ladder, is a metal, not a metalloid. So that should be easy to remember since most of us are familiar with aluminum. So any of these elements, when they're just in their pure elemental form, are going to be held together by metallic bonding. So magnesium solid will be held together by metallic bonding. Vanadium solid will be held together by metallic bonding. Osmium solid will be held together by metallic bonding, so on and so forth. Even mercury, which is the only liquid metal at room temperature, is held together with ionic or metallic bonding. So again, we're not talking about compounds here, we're talking about individual metals in their elemental form. So when we look at these metals, metallic bonding does have a very precise definition that we need to know. Metallic bonding is defined as the electrostatic attraction between positive ions and delocalized electrons. Why? When we have metal atoms come together, and we're going to look at this diagram right here. When we have the metal atoms come together, those atoms are formed over a nucleus and then the cloud of electrons, just like any other element. But when they come together to form the actual metal, so the bar of gold or the wire of copper or the bar of magnesium, those atoms are going to lose their outer or some of their outer electrons. So this electron will be lost by this atom, this electron will be lost by this atom, this electron will be lost by this atom, so on and so forth, similar to what happens to the metals in ionic bonding. Well, the problem is that unlike ionic bonding, where there's a non-metal to pick up the electron, in metallic bonding, nothing is there to pick up those electrons. So what happens to these electrons? The electrons that those metals form are going to be delocalized. And this is a very important word to use. We used the term sea of electrons when we were in honors chemistry. We're no longer going to do that. We're going to use an appropriate term, which is delocalized electrons. So the electrons that are lost by the atoms are going to essentially flow in between the ions that are now formed. Because whenever those metals lose electrons, they form ions. So those cations formed by the metal are going to create the points in the lattice of the metal, of the solid lattice, and then in between them, these electrons that they lost are going to flow, which we call the delocalized electrons. That's why, if we look at the definition of metallic bonding, the definition of metallic bonding says the electrostatic attraction, remember, electrostatic is the same as saying magnetic. So the electrostatic or magnetic attraction between positive ions, the positive cations are formed by the loss of the electrons, and the localized electrons, the electrons themselves. So essentially, the attraction that these negative electrons that are flowing around the cations have for the cations themselves act like a glue that holds all the cations together. Because those negative electrons are attracted to the positive cations and vice versa, holding this whole structure or magnetic or metallic lattice together. It's very important when you're asked for these definitions to use the appropriate terminology. The localized electrons, not just sea of electrons. The electrons that are shared by all the metal ions are again called delocalized or mobile electrons, which are electrons that are not associated with any particular atom. So because these electrons are flowing and they're moving around, they're not belonging to or they're not associated with any one of these cations. So this electron right here does not belong to this cation or this cation or this cation. It is free to move around and flow in between all the cations. So it is delocalized. We're going to use this word a lot later on in chapter 5 because there are other forms of matter that have delocalized electrons that we're going to study. This is the first, metals are the first of these instances that we see where the electrons are delocalized. In something like ionic bonding or covalent bonding, the electrons are not delocalized, we say they're localized because they belong either to two atoms only or to one cation or one anion in ionic bonding, whereas here these electrons are free to flow around the whole metal and therefore that's why we call them delocalized. Now if you look at this diagram, you will be asked to draw out this diagram. You have to be careful with something when you draw the diagrams. Obviously, the base of the diagram is fairly easy. We have the cations in some kind of repeating pattern in a lattice, and then the electrons flowing in between them. But one of the things that you need to also think about is the ratios of the cations to the electrons. So let's think about that a little. Imagine if we are drawing the diagram for two different metals. Sodium, so we're asked to draw a sodium metal diagram, and we're asked to draw a magnesium solid diagram. And we're asked to draw the metallic bonding in them. When we draw the sodium diagram, we'll draw our sodium cations. And these are going to be cations, meaning that we'll put here a little drawing that a circle means Na plus cation. And then in between them, we'll put the electrons. 1, 2, 3, 4, 5, 6, 7, 8. And we'll put this one right here. Now, why am I drawing 8 electrons specifically? Well, if you notice, and I will put again here a little key, that line means electron. If we look at this, we have that we are doing this for sodium. When a sodium atom loses electrons to become a sodium plus 1 cation, it loses 1 electron to do so because the charge of the sodium cation is plus 1. Meaning that for every 1 sodium atom that we have, we create 1 sodium anion and 1 electron. So the ratio between the sodium cation and the electron is a 1-to-1 ratio. So when we draw this, we need to make sure that we are drawing that ratio. We have 1, 2, 3, 4, 5, 6, 7, 8 cations that we have drawn, and therefore we need to make sure that we have 8 electrons because of that 1-to-1 ratio. So 1, 2, 3, 4, 5, 6, 7, 8 electrons in total. So here we are making sure that we have and we're keeping the 1-to-1 ratio between the sodium cation and the electrons. Now, when we do this for other metals that don't have a 1-to-1 ratio, we need to be careful. Because let's say we're drawing the same thing for the magnesium element. Magnesium does not have a +1 ion normally. Magnesium, being a group 2 element, forms magnesium 2+. Well, since for every one magnesium, we form one magnesium 2+, but because of that 2+ charge, that magnesium, in order to do this, is losing 2 electrons. Meaning the ratio between the ion and the electrons is not 1-to-1 like it was for sodium. It is a 1-to-2 ratio. So here, when we draw this diagram, again, we're going to make a little key, put that the circles are magnesium 2+, and that the lines are electrons. And when we draw this diagram, we're going to again draw 1, 2, 3, 4, 5, 6, 7, 8 different magnesium ions, and you could draw more, you could draw less. You just need to show that they are in some form of pattern. But when we draw the electrons, because of this 1-to-2 ratio, we're not going to draw 8 electrons, we're going to draw 16 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, we'll draw 15, and 16. So here we're drawing 16 electrons and 8 magnesium 2+, whereas for sodium we drew 8 electrons for the 8 sodium +1. And that all has to do with the charge of the ion. Because the natural charge of sodium is a +1, there's a 1-to-1 ratio between the ions and the electrons. But because for magnesium, there is a 1-to-2 ratio because of the 2+ charge, then we have to draw twice as many electrons as we do magnesium ions. If we're doing this for aluminum, which is a 3+ charge, then there will need to be 3 electrons for every 1 aluminum ion. So be very careful because the general structure is not that difficult. It's just a repeating set of cations with electrons in between them. But you need to keep in mind the ratio that is based between the ions and the electrons, which is based on the charge of that ion and how many electrons it releases. All right. Let's go back to our PowerPoint. So, metallic bond strength and physical properties. Because of the metallic bond, there are certain physical properties of metals that we get because the metallic bond is what it is. The strength of the metallic bond, for example, is going to increase based on 3 factors. So there are 3 things that affect the strength of the metallic bond. One is the increasing positive charge of the ions. So this is very simple. The more highly charged the ion is, the more the localized electrons per ion you get. And so number 1 and 2 here are actually tied together. That's why they're in the same color. Number 1, increasing positive charge of the ion. Number 2, increasing number of the localized electrons. Well, like we just discussed, if we have Mg2+, a higher charge, we get more electrons. Let me just draw it this way. For every magnesium 2+ ion that we have, that is going to be equivalent to 2 electrons, where if we have sodium +1, a smaller charge, we only get 1 electron. So these two are tied together. And why does this mean a stronger bond? Well, that's very simple. The higher the charge of 2 charged particles, and the larger the number of those particles that you have, the stronger the attraction is going to be. So magnesium will have a stronger attraction than sodium will because of the sheer numbers and size of the charge. Because this is 1+ and only 1 electron per 1 plus. This is 2 plus with 2 electrons per 2 plus. This is going to have a stronger pull and therefore a stronger metallic bond. Also, the other thing that will affect the size of the ions, or sorry, the strength of the bond, is the size of the metal ions in that lattice. And this is very similar to what we discussed earlier with covalent bonding and ionic bonding. Essentially, the positive charge from an anion comes from its nucleus. The closer the nucleus is to the localized electrons, the stronger our bond. So if we have something like, let's compare lithium and sodium. If we have something like lithium, which is smaller, and let me actually make this actually smaller. If we have something like lithium, which is smaller in size than sodium, which is larger in size, those electrons that are delocalized, that are floating around this atom, are going to be closer to the nucleus of the atom for lithium than they are for sodium. The distance from the delocalized electrons to the nucleus of sodium, which is where that positive charge is coming from, is larger than it is for something like lithium, which is a smaller distance because of a smaller ionic radius. And because of that, the larger the distance, the weaker the bond. Decreasing sizes of the metal ions are going to get us stronger bonds. So the bond in lithium metal will be stronger than the bond in sodium metal simply because of the size, because both lithium and sodium form +1 ions, are both group 1 elements. So we can compare the strength of the metallic bond based on those two factors, the charge and the size. The higher the charge, the stronger the bond, because it also means more delocalized electrons. The smaller the size, the stronger the bond, because the delocalized electrons are going to be closer to the nucleus, which they're attracted to. Now, that strength in bond difference is going to also affect the physical properties of the metals, mainly melting and boiling point. The higher the strength of the metallic bond, the higher the melting and boiling point of the metal will be. Very simply because it's going to take more energy to set them apart, right? It makes sense. If these are closer and therefore more strongly attracted, or if there's a higher charge and the electrons are more strongly attracted, the metallic bond is stronger. It means it's going to take a lot more energy to separate those metal ions from each other, and therefore the boiling point and melting point are going to be much higher. So let's compare these three elements: sodium, lithium, and magnesium. Let's compare sodium and lithium, which is this first. Lithium has a ion size of 90 picometers, so smaller, whereas sodium has an ion size of 116 picometers, much larger. They both have a +1 charge, so because the charge is the same, we can just mention that the charge is the same, so we look at size. And because lithium is smaller, the metallic bonds in lithium are going to be stronger. And we can see that in the melting point of the metal. Lithium has a melting point of 181 degrees Celsius, whereas sodium has a melting point of 98 degrees Celsius, almost half. Why is that the case? Because lithium has stronger metallic bonds than sodium, because lithium has a smaller ionic radius than sodium does. And therefore its delocalized electrons are closer to the nuclei of the cations, which leads to a stronger bond. If we look at now the difference between lithium and magnesium, now the sizes of lithium and magnesium are relatively the same. Lithium has an ion size of 90 picometers, whereas magnesium has an ion size of 86 picometers. So the sizes are relatively equivalent, so they're not going to affect the bond strength too much. But if we look at the ion charge, which is actually a more prominent feature, so the charge of the ions actually affects the bond strength more than the size does. If we look at the ion charge, magnesium has a 2+ charge, whereas lithium has a 1+ charge. This difference in charge, even though their ion sizes are relatively the same, that difference in charge is what leads to the difference in melting points. The melting point of magnesium is almost 5 times larger than that of lithium. It's 650 degrees Celsius. Again, why? Not because of the ion size, because they're relatively the same, but because of the more prominent difference in ion charge. Magnesium having a 2+ charge means that it will have a stronger bond, metallic bond, than the lithium, and that can be seen in the difference in its melting points. So this is something that you should keep in mind because you will be asked to make those comparisons. Now, another property of metals that comes from their structure is their electrical conductivity. And this is a little farther or easier to understand. Metallic bonds are only type of bonds that are reliably conduct electricity. Now, what does that mean? All metals conduct electricity. There's very few covalent compounds that conduct electricity, and no ionic compounds conduct electricity when they're in the solid state. But all metals conduct electricity, and this is due to their structure that we just looked at. The delocalized electrons in the metal serve as a space where electricity can flow. Something that you might not be aware of is that electricity is just electrons flowing through a wire. So if we have something like a copper wire, I'll make it reddish. If we have something like a copper wire, going from, let's say, the outlet to your TV, that electricity that flows from the outlet to your TV is actually just a flow of electrons. Electrons in this metal wire are flowing from the wall all the way to your TV. That flow of electrons is what we call electricity. So what makes things be able to conduct electricity? Well, for something to conduct electricity, it needs a space or some form of conduit that can grab those electrons and carry them through. In the case of a metal, that's pretty simple, because in the case of a metal, electricity simply flows through the delocalized electrons. All those electrons are kind of pushed through like water in a pipe. They use those delocalized electron spaces to push electrons along and create that flow of electrons that we call electricity. Metals are the only chemicals that conduct electricity in the solid state as a group. There are exceptions to this. There are some covalently bonded compounds like graphite and graphene that can conduct electricity, but we will discuss those in chapter 5. For now, metals as a group are the only generalized group of chemicals that can conduct electricity thanks to the structure of their metallic bonding. So let's just recap all of this with a quick question from the paper 2 AICE exam. Describe the metallic bonding in gold. So there are specific things that you want to say when you're asked to describe. Because notice, it's a definition or a statement, right? Describe does not mean define. It does not mean state. It means to show the workings of something. So it's not always going to be just a simple writing down the definition. So when we describe metallic bonding, we are trying to describe very specifically in gold the bonding, and we are specifically doing this for gold. So we will have to, in this, address the gold and address metallic bonding. Now, bonding is not the losing of the electrons, it is the attraction of the electrons. So one of the keywords we'll probably have to mention is attraction of the delocalized electrons for the, and again, be specific with gold, for the Au plus ions. So the gold plus 1 ions, or if you didn't know what the charge was, you could just say the gold ions, right? Either or. So that's one thing that we're probably going to have to discuss. But then the other one will be, because this is 2 points, so this alone wouldn't get us all the points. The other one would be, where do those ions come from? So we have two options here. We could say that the delocalized electrons come from the electrons that the gold lost. So we can say something along the lines of comes from Au losing electrons and becoming Au plus and electrons. We could also, if you notice where I'm writing, there's a big empty space here. So we could actually draw a diagram for the structure of the gold atoms. And anytime they give you space like this, that's usually what they want you to do. Even if they don't state it, it just says describe, we can use a drawing to describe that the localized electrons and the gold ions. And then we could use arrows to show the attraction between the two, which is the metallic bond. So we could do this in a number of ways. The important things here, if we look at the mark scheme, is for us to specifically mention the attraction or hold and the fact that it's between positive ions. So positive ions, or I should have used the word cation here, but I did say Au plus, so that will show it's a positive ion. And the delocalized electron. So again, notice a very important word, delocalized. I wrote it with the English Z. But if you write it with a British S, it will be fine either way. But notice how it says may be seen in a label diagram. So you didn't need the diagram in order to get full points on this question, but it is one of the ways that you could have shown this. So there's a number of ways of answering this question that will get you both points, but these are the important things. That you mention the attraction or hold because that is what the bond is. And that you mentioned positive ions, because again, we're talking about gold specifically, and the localized electrons with that particular word, the localized, in there. All right. So that's it. Again, metallic bonding is not a huge topic on the exam. It is a very small, narrow topic, but it is one that you should master because it's a way of getting easy points. That is it for section 6 of chapter 4. I'll see you all in the next video.